Recording. So it's our pleasure to have Sasha Monin here with us today. He will talk about multiparticle processes, large charge and semiclassics. So thanks again for agreeing to give the talk, and the floor is yours.
Okay, thanks a lot. It's always a pleasure to give the presentation in Minnesota, although not in person, via Zoom. Yeah, still. So my talk is going to be about multiparticle processes and semiclassics, and this is somewhat a continuation of our work that I already presented a couple of years ago in Minnesota about large charge CFT. So this work was done in collaboration with two students. It's Gilles Badel and Gabriel Cuomo, who is now in Stony Brook, and with Riccardo Ratazzi. So yeah, let me start from the introduction and to give some motivation for this work. So I think we can argue that perturbation theory is the only generic tool that we have for addressing field theories or quantum field theories at the moment. Of course, there are other tools like lattice simulations and so on and so forth. But I mean, if it's analytic, then this is the only generic one. Others may also be there, but they're mostly used for very specific theories. But for generic ones, it's the perturbation theory. However, the problem with perturbation theory is that it doesn't cover all the theories that we want to. And in many cases, it breaks down. So what are the cases when it breaks down? It's either when the coupling is strong and we cannot just trust our perturbative expansion period, or even when the coupling is small and we go to sufficiently high order in perturbation theory, usually terms at higher order in perturbation theory start to grow, and suppression due to the small coupling is not enough already to beat the multiplicity or the multiplicity of those contributions. And that basically signals that in usual setups, that perturbation theory is not a convergent series, but only an asymptotic series. Nevertheless, we do believe that for small coupling, it is still possible to recast somehow, to reorganize this perturbative expansion so that it is still can be trusted. In what way? So basically, what we're interested in is to consider a theory with a very small coupling with sufficiently large number n, be it high order in perturbation theory or just large number of particles that are involved in the process. And we want to consider a double scaling limit when lambda n is constant. So this is like similar to Toth coupling. So, yes. So just the illustration. So the whole idea of my presentation is very, very simple. Let's consider the following integral, just a regular integral, one-dimensional integral. I'm trying to compute the analog of expectation value of x to the power 2n in a theory of lambda x to the 4. So this is the leading term. I do not know if you see my pointer. I hope you do. So is the—
I do see the pointer.
Yep. So this is the standard Gaussian factor minus lambda x to the 4, and we assume that lambda is small. How can we do this integral? We can of course do it explicitly, but let's not trick ourselves. What we can do, we can simply expand in powers of lambda, and of course the leading contribution is going to be just one gamma function of n plus 1/2. Then the correction is lambda over 2 gamma of n plus 5/2, and so on and so forth. So we see immediately that for sufficiently large n, since gamma of n plus 5/2 goes like n square of gamma of n plus 1/2, this series cannot be trusted as soon as lambda n square is of order 1. So this is just signals that this series is not asymptotic, is not convergent, it's just asymptotic, as we know, because in here already for lambda negative, this integral does not exist. So basically the function f of lambda n is not regular at lambda equals 0. So what do we do here? We can resum actually the leading terms in here, if we take into account just the leading terms in n, then we can resum it to the exponent, and actually the form of this function, it has the following form, plus of course corrections lambda n cube and so on and so forth in the exponent. So we see that actually perturbation theory breaks down not for lambda n square of order 1, but actually for lambda n of order 1, but still the breaking is there. However, looking at this expression, we may guess, look, the function f of lambda n should have the following structure. It's just the overall gamma function of n plus 1/2. Then it's n factor times some function of lambda n. Then it's f0 of lambda n, 1 over n, f1 of lambda n, and so on and so forth. Okay, and what we're computing in here, this is just the couple of first coefficients of expansion of f minus 1 twiddle of lambda n for basically, these are just two first coefficients. Right, similarly, we can write it as a function, not expansion in n, but in 1 over lambda. So it's 1 over lambda f minus 1 of lambda n, and so on and so forth. Okay, so how can we prove this, that this is indeed the case? It's pretty simple. We can do the following thing. We can just say that what we're computing, instead of expanding this exponent in powers of lambda right away, so basically computing this integral in the saddle point method around 0, here let's exponentiate this x to the power 2n, and what we have here is n log x squared, and let's find a new saddle that corresponds already to this exponential. And as we can see here, if we factor out 1 over lambda in the exponent, we rescale x, we see immediately that yes, indeed, this function depends only on lambda n, and of course saddle point tells us that expansion runs in powers of lambda, as it should be, right? In the powers of coupling, but all the coefficients are fixed powers of lambda n. Now, finding the saddle point and computing this integral via the saddle point method, we will capture all of these coefficients in a systematic manner.
So I have a question here. So here, you said you rescaled x. So does that mean that you're going to require some kind of scaling invariance for this method to work later on, or
no? This one I just rescaled, meaning that it's 1 over lambda. That I wrote my variable of integration. It was x, and now it's square root of lambda x.
I see.
No,
okay. So you're not going to require conformal invariance later on.
I will require conformal invariance only for specific purposes, but this one is not related to this rescaling.
Oh, okay.
It's only that what I would like to demonstrate is easier to do in conformal field theory, but the general method should work regardless of whether it's conformal or not. I'm not demanding that by rescaling my integral stays the same. You see that right. That's what comes from the measure, and from the rescaling it's here.
Yeah, I see.
Yeah, but it is just kind of changing your variable of integration. Yeah. It's not a symmetry. It's just
but this is what I'm saying. Yes.
Yeah.
So now I'm coming to the outline of my presentation. I'm going to be focusing only on scalar field theory. At first, I start from a real scalar, and I discuss what is known about these theories, and in particular about amplitudes or cross sections for large number of particles involved. I'll tell you about the results for small lambda n. We discuss the relevance of classical solutions. We discuss the limit when lambda n is large, some subtleties there, and then to demonstrate how it works on a more solid ground and in a more clear-cut picture, I'll discuss again scalar field theory already now for a complex field with an additional O2 symmetry, and I'm going to be considering it at a Wilson-Fisher fixed point. So here I will consider conformal field theories, but this is only to make my life easier, just to show how the method works, not for the purposes of rescaling. And there we will be computing correlators of charged operators for actually for arbitrary n, but in particular, we'll be interested in large n. So actually what we will be computing is correlators of operators with large U1 charge or O2 charge. Yes, now I continue. So let me start from just giving you a couple of points about what is known about amplitudes in this theory that I just mentioned. In this one, sometimes we will be considering theories with negative m, sometimes with positive. So with either in a broken or unbroken theory with broken or unbroken Z2. So let's start from computing just the endpoint function. This is completely unphysical because I'm here. It's f phi twiddle is just a Fourier transform of our field at 0 momentum. So to compute this correlator, it's easy just to find a derivative of the partition function, and the partition function is given by this expression. Now, since the log of the partition function can be expanded by definition like this, right? It tells us immediately that singularities of the partition function tell us the behavior of those coefficients Cn, but those coefficients Cn are nothing else.
Sash, but it is it's neutral field, right, or what?
Yeah, this is a neutral field.
Okay. And why it's tilde? What means tilde?
This is the Fourier transform.
So, sorry?
This is the no, this is not the Fourier transform. I'm sorry. This is possibly for tilde is maybe not the field itself. This is the fluctuation of the field. So if we are in an unbroken phase, then phi is just a field. And if we are in a broken phase, it's phi minus v minus vev.
Okay, I got it. But and argument 0. So you imply that it is g. What means 0? It is a space point, or what is 0?
Yes, this is yes. I think. Hold on, just 1 second. Yes, I think still, yeah, phi of 0. It should be. No, the way it's written now.
It looks like momentum now.
Yes, 0 is a momentum. Yes, it's a p equals 0. Phi twiddle is the Fourier transform of the fluctuation.
I see. Okay, so
yes.
0 refers to momentum.
Yes, 0 is the momentum.
I see.
Exactly.
Then the integral of phi of x dx is phi twiddle of 0, right?
Yeah.
Yes, exactly.
But it implies
yes,
that
phi twiddle of 0.
So it implies that J is also not function of x, right? So it means that
Arkady, it's written here. J is just a constant.
Right. It's what I am asking. Yeah.
Yeah. This is what. Yeah. So phi twiddle is the fluctuation, is the Fourier of the fluctuation, and here it Here it should be actually not phi of x. It should be phi of x minus v if v is not 0 minus v. Okay, but the log. Yes. Now I'm just saying that the singularity of the partition function tells us immediately what the behavior of Cn is. Obviously, if we have singularity at Js, it means that Cn goes as n factorial times Js to the minus n. Right? Okay, so since we know that singularity of Z of J is n independent, we immediately know that amplitudes grow factorially with n. And the exact position, as I said, of the singularity tells us the lambda dependence. For this theory, it's easy to find the position of singularity. We just have to find where the solution for the stationarity equation, the two solutions coincide, and you can convince yourself it's just for v double prime of phi of Js is 0, and Js is the inversely proportional to lambda. So the bottom line is Cn goes as n factorial times lambda to the power n over 2. But this is what we would expect, right? In order to draw at tree level, all the diagrams that would contribute to n particle and endpoint function, we need to, yeah, it's going to be n factorial times lambda to the power n over 2. Okay, slightly less non-trivial amplitude, or slightly more physical amplitude, is now the following matrix element. Imagine that I consider the matrix element of the operator phi of 0. Now this 0 corresponds to x, and this is phi of 0 computed between the vacuum and particle state. Okay, so and all the particles are at threshold. I'm studying only amplitude at threshold. Now pictorially, it can be just written like this, and we denote it with just index n. And actually, you can write a recursion relation for this amplitude, and which is just delta of n1 plus n2 plus n3. That should be summed to n, right? And I have to sum over all n1, n2, and n3. Obviously, they should be odd, and summing recursion relation. This is your amplitude an at threshold, right?
But this amplitude is this not exactly the same correlator, right? Because it implies that g is function of time, right? It's not function of x. But
yes, absolutely. This is not the same as, look, yeah. I'm not claiming that Cn is equal to An.
Yeah.
An is a completely different thing. It's a completely different animal. So it's only to illustrate that whenever many particles are involved, it goes as n factorial, and still lambda to the power n over 2. For n large, it doesn't matter whether it's n minus 1 over 2 or n over 2. All right, so now going back to what Arkady just said, the way to compute this an, not from the recursion relation, why would that be interesting, is to show another approach is through the LSZ, right? We take an, we compute what we have to do. We have to compute correlator of phi 1 and so on, phi n with phi of x. Then we have to amputate all the propagators and take the limit p square to m square. And that's basically it, right? And that, well, of course, first compute the Fourier transform and then amputate the, just the standard procedure. The correlators, again, can be found by modifying the Lagrangian by shifting rho phi. And now rho should depend only on time. And we take it in this form. Rho of t is just rho 0 e to the I omega t. We do not have to take the source to be a function of x because we're not interested in spatial momentum. Spatial momentum is 0. So that's what we're interested is to find the expectation value, or a classical, yeah, I would rather say at this stage, it's just the expectation value of the field phi with in a theory with the source given by.
Is spatial momentum possible in a vacuum of particles?
I don't think it's related to the vacuum. It's related to what state I'm considering here.
Okay.
Right. I can take the momentum to be not m and spatial 0, so I can take it not at threshold, but I can take it at p1, p2, whatever. Right. So if I wanted to consider non-zero spatial momentum for all particles, then I would be forced to consider also correlators that are not sourced by just time-dependent source. Okay, so the leading contribution obviously comes from just solving the classical equations of motion with a source, right? So classical equation of motion is given, you can convince yourself that it's given by the following series, Cn z to the power n, with z is rho 0 divided by m squared minus omega squared. You can convince yourself in the following way. If you drop this interaction term, then for phi 0, it's precisely rho 0 over m squared minus omega squared, but then corrections can be taken iteratively into account, and that generates z squared, z cubed, and so on and so forth. Okay, now using the LSZ, what has to be done, we just have to differentiate. Here we just said what we have to do. We have to differentiate with respect to rho, but in the end, it boils down just to differentiating with respect to z, and then to set z to 0, which corresponds to setting rho 0 to 0. Therefore, what we're looking for is to find solution to this equation, however, with the tricky boundary conditions, so that at Euclidean time of minus it, it goes as mt. So it's just the statement that phi 0 of t goes as z to the power z1 plus z squared and so on and so forth. But we have to solve just this equation.
But in terms of diagram, it is just a three-level diagram.
Yeah,
right?
these are only three-level diagrams. That would correspond only to what we discussed just 5 minutes ago. So solving this equation, this is the solution, and then the amplitude is given by this function. This is for an unbroken theory, and this is for a broken theory, which corresponds to almost identical expression. And of course, this expression it reproduces what has been computed just solving recursion relations. All right, now, Arkady, you always ask questions one slide before. So now, what would you do if you wanted to take into account more, say, one loop? At one loop, obviously, this is just a combinatorics. Combinatorics tells you that you can take some lines, put them together, and then they go out again. So it's just n times n minus 1, right? So n legs you can pair with n minus 1 legs. So the coefficient actually for, not the coefficient, but the full one loop amplitude, again, still at threshold, can be written the following way. It's the tree amplitude times 1 plus some coefficient lambda n squared. For n large, it's n minus 1. Right, so this is what we see for sufficiently large n, precisely for 1 over square root of lambda, perturbativity is lost, right? So we cannot trust perturbative result anymore. But actually now, in the similar manner as we discussed for regular integral, if we resum the leading n terms, what can be shown that actually the amplitude is given as 1 over 2 lambda log lambda n minus lambda n plus this coefficient. So this log lambda n, it comes only just from the factorial, and that's it. And lambda comes from the tree amplitude, and this b1 is precisely this b1, which exponentiates. So from here we see that perturbativity is slightly extended. It breaks down not at n of order 1 over square root of lambda, but it breaks down at 1 over lambda. But still, as before, perturbation theory cannot be trusted for arbitrary large n. So what should be done for large n? It has been done by Voloshin and Gorsky. They considered it, they found a different solution, not this one, but for that corresponds to the limit lambda large lambda n, and they found that the scaling of the threshold amplitude is now 1 over lambda and lambda n to the power 3/2. Okay, other things that can be computed is corrections due to being for particles being slightly off threshold. If we consider the process not at energy precisely n times m, but at energy slightly larger than n times m, then we can define kinetic energy per particle and per mass in the following way, and that has also been computed, and that corresponds to the amplitude of epsilon is, yep.
Sash, but
yeah, Arkady?
Yeah, this expression, it's for, I'm not sure, it's for large lambda n. I wonder,
no,
I mean, my question is, because if it would be just large lambda, then I would be questioning this, no, I mean, UV.
No. Lambda is always small.
Yeah. So in this way, you are not touching you. This solution does not touch you.
No.
Right?
I'm
in this sense.
no.
Okay.
No, I'm small lambda.
I see. So
I'm just playing only with the number of particles. I'm just increasing the number of.
I see. I see. Okay, so you are not going to touch UV. I mean, sensitivity of the theory, right? In this sense.
No.
Sasha, I have a question.
In this sense,
go ahead.
No, I wonder that in this way, I wonder whether you consider, say, different dimensions, right? Because this will, is it important that dimension is, say, 3+1, or it's not important for you?
Dimension that is 3 plus. No, here I'm considering only. This is just a physical thing. It's 3 plus 1.
Yeah, I understand. Yeah, right. But,
yes,
but
for 3 dimensions, it's going to be IR, very IR sensitive. There will be some divergences, and I do not want to go there.
You mean what means for 3 dimension?
In 2 plus 1.
In 2 plus 1, I see.
Yeah, in 2 plus 1.
Hi, Sasha. Just to understand, for the results in these 2 slides, those are all calculations done in the unbroken phase, right?
This one is done in a broken phase. These 2 results. This is for the it's not even phase. It's unbroken theory. This is broken theory. The result corresponds to the broken theory. And for large lambda n, this is only in broken theory. What broken
can you go back 1 slide?
Sure.
Slide 12. This result is in the unbroken phase, right? Unbroken
this
theory.
One is in an unbroken theory, but it's similar. In a broken theory, it's similar. It's only that this coefficient is slightly different.
Okay, and then can you go back 1 slide, which is the tree level result?
Sure.
Can you explain to me, what's the difference between the unbroken and the broken one, and why they are so similar? Is it because in the broken one, the leading contribution piece is still the 4-point interaction, where with no mass insertions, etc. So that's why the results are the same.
Why the results are the same? Look, I don't think I have an argument for why the results are the same. It's just what would you expect? You do expect that the amplitude should grow exponentially with n, or factorial with n factorial.
Sorry. I'm from a constructive point of view, right? So the unbroken one only have the 4-point interactions. In the broken one, start to have 3-point interactions.
But they conspire in such a way so that to consider. Yeah, look, if you wish, this one works only for n equal to 2k plus 1, and this one works for all of them, right? So in this sense, they are different. And this is precisely due to manifestation that we have phi to the 4 interaction and phi cube interaction, and here, and Z2 can be broken, while here Z2 should be preserved.
Right, but even in setting n equals 2k plus 1, for both cases, we are saying the amplitudes for those 2 cases are really close to each other. That means the 3-point interactions plays no roles at tree level for those amplitudes.
No, it does play a role. It does play a role because, look, just go to n not equal to 2k plus 1, and then you see that it does play a role.
Sure. But I want 2k plus 1 just to compare. So for the same.
Sure, but it's not that they disappear. It's that they contribute in such a way so that all the combination gets to the similar result.
Yeah, which from a constructive point of view, that means the 3-point functions plays no role when n equals 2k plus 1.
Look, I think I'm hesitant to say that it plays no role simply by the fact that results are similar. In the construction, just if you do the same construction as we did here, just solving recursion relation, then it is important to take into account 3-particle interaction. They would also contribute. Okay, so it's not that I drop them and then the result follows. So you see, if we go into details, then the coefficient 8 here is not the same as coefficient 2 here, and so on and so forth. So the fact that they all give similar structure doesn't mean that 3-point interactions contribute. Okay.
Sure. But I think later on you're probably going to tell us in the unbroken one it's the theory converges, the other one it blows up, right? But okay, let's save for later.
Okay. Yeah. So what I was trying to get here at is the structure of this term, even when we take into account off-threshold corrections, it's still of the same form as lambda n times epsilon over lambda. And that looks very much semiclassical, the same as this one, and similar to the previous result. It's just some semiclassical function that I will get soon there. But before that, I just want to make one comment. So instead of computing just the amplitude, we can call it, people call it by different names, like cross-section or rate. I think I prefer to call it just n-particle contribution to the spectral density. So instead of computing just the amplitude, I compute the absolute value of the amplitude squared and I integrate over the phase space. So I compute the inclusive quantity. So that can correspond to, say, 2 to 2 if I couple my field phi to some other, say, phi square or chi squared, then it's 2 to 2 into n, not 2 to 2 particle into n, right? And at the same time, this is just that the spectral density is given by the sum of all n-particle spectral densities. Okay, and the way to compute this n-particle spectral density, I just compute for small epsilon. Obviously, the leading contribution will come only from the phase space, right? I can take my amplitude at threshold, compute the absolute value squared times the appropriate factor of epsilon to the power 3n over 2, right? This is just the power of the volume of my phase space. Now, looking at this expression, we can say that rho actually behaves as 1 over lambda times some function of lambda n of epsilon. And that conjecture was proposed by Libanov, Rubakov, Son, and Troitsky in '94. And more generally, of course, it should be similar to what we had for regular integral. It's 1 over lambda, f minus 1 of lambda n, f0 of lambda n, lambda, and so on and so forth. So for small lambda n and small, yep.
The reason that such high power of epsilon appears is one of the reasons is there's no long range interaction, right? Because if there would be charged particles, like the two charged particles at the threshold, the phase space is not suppressed by their small velocity relative to each other, right?
The phase space is not suppressed by small. No, if I take n particles almost at rest, I can compute my phase space is going to be precisely this, right? It doesn't matter whether particles are charged.
What I'm saying is I take n equals 2 and the two particles at the threshold that interact due to the long range force, the Coulomb. Then it starts from where your plane waves are no longer asymptotic states, and that scaling would be different, right? It would start from constant, not from epsilon. It doesn't matter. Here,
no, the phase space. No.
There is no long-range interaction. Only
right. No long-range
very
interaction.
close to the threshold. So no carriers. I mean,
you know, it becomes a singular velocity when you have Coulomb between particles, and it compensates this phase space. Right?
Mm-hmm. Okay. All right, so for small lambda n and small epsilon, we just computed this f minus 1 that corresponds to 3 level, 1 loop, phase space, and so on. For large lambda n, this is the result that I just discussed, derived by Voloshin and Gorsky, plus the same phase space, plus whatever unknown. And there are no results for large or not very small epsilon up to now.
it reminds me Sasha, it reminds me very much the situation with this Faleron in Young Mills when people.
Yeah, but I think it's precisely
The same.
that.
This function in Young Mills is called Holy Grail function and
Yes.
has very similar expansion.
Yes, but I think the interest in studying scalar field theories, it stems, of course, from Falerons and from gauge theory.
Yeah. No,
Okay.
but it's already, it was demonstrated, Mish, when he showed that instead of lambda n squared, it becomes lambda n. You see, it was a similar effect there. I mean, that, that when you exponentiation, then you are getting different, behavior.
Mm-hmm. So basically, I'm just repeating myself. So the form of this result suggests that there is a semi-classical approach that can capture the result. And this approach should be valid for lambda small and large and lambda n fixed and epsilon fixed. Also, there is a proof by Son and company that actually the factor f minus 1, the leading one in here, it's insensitive to whether we compute, say, expectation value of phi of 0, or we compute phi square of 0, and so on and so forth. Right? So as long as phi is not to an arbitrary large number, it doesn't matter whether we compute phi of 0 or phi square or phi cube. Therefore, Son comes up.
But here should be some coefficient as well, because phi square, even by dimension, different from phi, right? Or what?
Look, but I call this of lambda. I'm just saying that.
No, I understand. Yeah.
Sure. The true statement,
I mean,
of course, I have to write it in proper dimensions, but the true statement is that exponential factor of this matrix element and exponential factor of this matrix element are the same. The pre-exponential factor is still lambda suppressed. That's why I put it into here.
Mm-hmm.
So what Son suggests is to do the following. So instead of computing expectation value of 0 and n, he computes directly for the cross section or for spectral density, but insertion in here is phi of 0. Is not phi of 0 or phi of 0 squared. He inserts either the j phi of 0. Okay, and in order to make the saddle point work, actually the scaling of j should be alpha over square root of lambda, and in the end, to remove this, so to say, large insertion of j, alpha is taken to 0. But this is just a technicality, which, if that was the only difficulty, that would be already a success. So now what has to be done, so as you see here the projection goes onto n particles and on states with energy E. That is implemented in terms of path integral by going to A and A dagger. And there are basically, you have to extremize your action with a proper boundary condition at j going to 0. And you have to solve classical equations of motion as Son showed. And these are the boundary conditions at t plus and minus infinity. And the extremization runs over all singular solutions or surfaces of singularities of those solutions, and then according to Son, you can get the proper result. And what he actually showed, that indeed for small lambda n and small epsilon, he indeed reproduced the result. He showed that his method is consistent with what has been derived before by what we discussed. Okay, I'm not going to show the example of large lambda n. If I have time, we can discuss it. But instead, what I wanted to say is the following. So the approach of Son is good, but I think you have to be a genius to understand it, because for me, I just cannot put it on a computer. It's not systematic. So you have to do this, you have to do that. And we wanted to have more robust construction, more like on a solid ground, when you have just a procedure, and you follow from A to Z, and everything is understood. So for that, we consider just O2 model in D equal 4 minus epsilon dimensions, and this is a conformal theory at Wilson-Fisher fixed point, and we will be considering what we're after is primarily just a 2-point function or dimensions of operators with large charge. Okay, later we will consider also other correlators, but primarily we need to find dimensions of operators with large charge. Okay, this is like the analog of what we consider. It's not one to many, but it's many to many, right? I create some state with large charge here, and I annihilate it into a state with another state with large charge M.
If it were not, excuse me, may I ask a question? If it were not for the vortices in this model, then there would be no interaction, right? Because locally it's a free field theory, right? D mu alpha squared.
I'm in 4 minus epsilon. I'm not in 4.
And then what?
4.
It's still
So
locally. Locally, O2 is.
It's not a free theory.
No, but O2 is like U1.
Yes.
So it's d mu alpha squared, I would write, but there are some.
No, d mu alpha squared minus lambda phi to the 4.
D mu alpha, and where is lambda to the 4th?
Yeah, no. This is what I'm getting to. So this is my theory. I'm considering a theory in 4 minus epsilon, and this is my theory. d phi plus lambda over 4 phi bar phi squared.
And phi is a complex field, right?
Phi is a complex field, yes.
So you have U1, okay. It's U1 in this sense. It's not a U1 sigma model.
No, it's not a sigma model.
It's
sigma
not
model
multi-dimensional.
What?
But in this way, Sasha, I wonder that when you consider this anomalous dimension of operator, there are 2 ways to do it. One is to do what you said. I mean, consider this correlator. Another way is just to consider like perturbation, and then you are not doubling operator, but that one, it should be consistent.
And it will be consistent.
Yeah. Okay. So usually.
Arkady, as I told you, you are asking a question just one slide before. It's here.
Okay.
It's pretty consistent. So look, in here, I just wanted to remind what I mean by Wilson-Fisher fixed point. Wilson-Fisher fixed point, I have to compute the beta function for lambda 0 for my coupling lambda, and computing the derivative of lambda with respect to log mu, I get it's d minus 4 times lambda times beta function for 4-dimensional theory, and therefore, if I set this expression to 0, I see that there is a fixed point for lambda star, which is equal to epsilon, right? If I solve this expression perturbatively, it's lambda star over 16 pi squared, epsilon over 5 plus 3 epsilon squared over 25, and so on. Okay, so it is weakly coupled fixed point. The trade-off is that I have to be in 4 minus epsilon. I'm not in 4. In 4 dimensions, it's a free theory. But in 4 minus epsilon, it's a weakly coupled theory. And of course, this is what we would say for epsilon equal 1 if we stretch the approach and use our imagination. This is the standard epsilon expansion for the Ising model, right? Okay, so the dimension of an operator, as I said, can be computed from the 2-point function, as in usual CFT, right? It's up to a constant, which can be reabsorbed into the definition of phi. It's 1 over xf minus xi to the power twice the dimension of the field phi. Classically, right, at the leading order, or just classically without taking into account any corrections, it's n times d over 2 minus 1. Right? Alternatively, as Arkady said, the way to compute the operator phi to the n, we just have to renormalize our composite operator by demanding that n-point function of composite operator with fundamental fields be finite, and that tells us how to find the z phi to the n. This is only one multiplicative renormalization because phi to the n doesn't mix with anything. Therefore, the anomalous dimension has to be computed, and it's given by just this expression, right? These are the standard ways to compute the anomalous dimension. Now, this is one loop, two loops. If you do the computation properly, blah, 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 that results in the following anomalous dimension. Okay, this is the full result. Okay. Now, the expansion, this expansion breaks down at obviously lambda n of order 16 pi squared, right? Because I see that it's lambda n here, it's already lambda n squared over 16 pi squared. And I can reorganize this expansion, not like this, but I would rather say that I factor out from here n, it's lambda n, and the same as here, lambda n, but this one is already not, this one is enhanced by n, and the next term is not enhanced by n. Okay, so that suggests just some semi-classical approximation, semi-classicality of this result, and I will show you why. So, but this is very similar to what happens with the RG, summation of large logs, right? I take lambda log is my parameter, and this one can be not small, but still lambda is small, and my result for RG is just some function of lambda log times lambda other function of lambda log, and so on and so forth.
So Sasha,
so how do we, yep.
I have a question here. So does this theory, because you're at large n, does it have a gravity dual then? Because you're doing a CFT as well?
Look, I think
that's what it reminds me of.
I think all CFTs should have gravity dual. Large N CFTs have weakly coupled dual, but this N is not a parameter of my model. This N is an external parameter, right? It's just a parameter of my correlator. It's not a parameter. It's not large number of flavors of or colors. I'm just computing this specific correlator. If I compute it like phi, then there is no large N.
Yeah, but this could be like some large n. I mean, the phi is it's just counting the degrees of freedom. They could all be encoded into some gauge boson, I guess, some large n gauge theory in principle. But
Tony, I don't know how to answer this question. My first response would be I don't think that there is a gravity dual, but look, we can discuss it.
So, Sash, I think that in certain sense, if you are trying to kind of visualize the picture, that what you are considering in the case of when the amplitude of the field is large, right? No, I'm substituting large field instead of large number n, I mean number of particle. And then, but when you consider duality, then this corresponds between large field in large, say, field of your theory and it's very different than the correspondence of duality, right? So because then you need to find out dual only for large field, right? In certain sense, and it is not clear what is it.
No, large field. What do you mean large field? But
no, because
I think
when I consider large n correlator, I would say that it is like taking external field to be, containing, take a coherent state. When you have, all particles of the same momenta, then it's equivalent to the large amplitude of the field. Is what I'm trying to suggest. Okay, so then it is theory where you are considering background to be, a large field of your theory, right?
Look, but
large number of particles or correlator correspond to calculation.
Arkady, in this case, I think it's not even about large number of the amplitude of the field. It's more about the phase. But the phase oscillates a lot. It's about it's large. It's charged, right? It's charged, so it's e to the phi.
No. But when phi charge is large, it is the same as to say the charge field is also has a large amplitude, right? Because I agree about what you said about phase.
Sure,
right?
the amplitude will also be large, but it's I'm going to be talking about this.
Yeah, no. It's amplitude is large, and your background has a large charge. in this sense.
Yeah.
Consider,
Yeah.
that you are sitting in the background with a large charge, okay, and it is, I believe, correspond to what you're saying. What I'm trying to say is that duality for this particular sector, it's not clear how to formulate, if there is any duality in this.
Arkady, I think that this is what I tried to tell to Tony, that this one is only for a specific, n is not a parameter of a theory. N is a parameter of a sector.
Yeah.
Of my theory of this correlator. All right. So how do I do this computation? I computed phi n bar phi n. I write it as a path integral, and I do exactly the same trick as we did for regular integral. I exponentiate phi to the n and phi bar to the n. I rescale phi by some lambda. It spits out some factor here. So now immediately we see that everything depends on lambda n. So the expectation that the result should be just a power expansion in lambda with coefficients functions of lambda n is justified, and as we saw, this is the case. Now what we have to do, we just have to extremize this action with those sources. Let's do it for small lambda n, then it can be done just like this. I neglect the interaction piece because phi should be small. Then it's d phi, d square phi is equal to this, d2 phi bar equal to that. Obviously, the solution is not real, but that's a standard thing. So phi 0 is just like a Coulomb interaction, Coulomb potential. Phi bar is another Coulomb potential with a different point of insertion, with the relation between coefficients C0 and C0 bar, just like this. So C0 is not fixed. It just corresponds to the fact that there is a zero mode. And then plugging it back, this is what we get. The whole prefactor is not that relevant because it can be reabsorbed in the redefinition of phi, what we call by renormalized operator, but this part is important, right? This is what we have. That's our classical result for the dimension, and this is the first correction in lambda n, right? Obviously, it's just a comment that it works only for large n because we have to use Stirling's formula. So what we got, if we look at the anomalous dimension in here, we got only the leading term in lambda n. We didn't get lambda n squared minus n. We got only lambda n squared, and that's it. So this is what was just an illustration. In general, solving these equations or the analog of these equations is hard. And what we do is just use the property of CFT, which is the operator state correspondence. It's just a statement that to any state in CFT, there corresponds just one operator. And to every operator, local operator, there is just one state. How it is formulated usually, it's formulated through the following construction. So imagine that I have a CFT on the plane and I quantize it not slicing in a standard way just in time, but since now in CFT I have dilations also with the symmetry, I'm going to be quantizing my system radially. And transition between one sphere and the other is the Hamiltonian corresponding to this transition is just the dilation. And then I can view this plane as actually a cylinder, as just a collection of those circles, right, parameterized by time. So R is e to the tau. So 0 corresponds to tau to minus infinity, and so on and so forth. So basically, the statement is the Hamiltonian on a cylinder is the same as dilation on the plane. So if I have the spectrum of my theory on the cylinder, I know the spectrum of operators on the plane. So how does it work? So just to illustrate, if you take free theory, you map it on a cylinder, you quantize it, you know what this is the spectrum, and obviously this is what I have. My operator phi hat on the cylinder, I can map it on the plane, and this is the correspondence. Look, energy is L plus 1/2. If you have a state with spin L, then energy is L plus 1/2, and this is what we have here. Vacuum corresponds to operator 1. A00 dagger is just phi of x. A01 is just a derivative. A11 is another derivative. acting twice is phi squared, and so on and so forth. And those are primaries, and there are descendants. Okay, but the bottom line is that any state corresponds to a cylinder, to an operator, and to every operator there is a state. So instead of computing what directly this two-point function, since we are after just the dimension of this operator, we can compute just the following amplitude, right? The following matrix element of the Hamiltonian on the cylinder, right? If we compute the Hamiltonian on the cylinder and we consider t to infinity, obviously that should give us just the lowest state with energy, the lowest state with charge n, right? If we sandwich e to the minus ht between states, arbitrary states with charge n, then for t to infinity limit, that would project on a state with fixed charge n and lowest lying state, right? And in this way, we can find the dimension of this operator because we assume that this operator is the lowest operator with charge n. Okay, how to do that? That I'm going to skip. So how to do that?
But Sash, I'm sorry.
Yes.
I'm kind of a little bit confused that when you consider dimension, it is kind of associated not with Hamiltonian but with dilatation, right?
Yes, but Hamiltonian on Hamiltonian,
yeah.
This one is the dilation, right?
It
so
is
look,
dilation in original theory. I see, because
yes,
this
just
way it
look
could
at
be dilation.
Yeah, this is exactly dilation. So if you consider what
so the spectrum we are talking about is not spectrum of energy, the spectrum of anomalous dimension, right?
Arkady, it's both. It's on the cylinder, it's a spectrum in terms of energy. On the plane is the spectrum of operators. So I'm just look at this picture. So
Right.
I can view. Right. So this is what I said. So energy. Imagine what is the energy of this state. The energy of this state of course, I forgot to say that we consider here 3 dimensions. The energy of this state is just 1/2. It's L plus 1/2, right? The spin of this state is 0, therefore it's just 1/2. What is the dimension of operator phi of x? It's 1/2. Again.
Yeah, okay, but in this way, the notion of Hamiltonian and dilation refers to kind of how to say to different dimension, or how I should view it. That in this way, your dimension in your original example is 4 minus epsilon, right? When you consider this case, you're already at epsilon equal 1, or how I mean.
No, Arkady, here this is just an illustration how it works.
Yeah.
But there in any number of dimensions, I would just have to look. Imagine if I not in 3 dimensions, then what changes here that I have to expand not in spherical harmonics Lm but spherical harmonics Lj, right? This is just to illustrate that to any state in any CFT, there is on a cylinder. You take a CFT, you put it in a cylinder, you compute a spectrum in terms of energies on the cylinder, and that would correspond to spectrum in terms of dimensions of the operator on the plane of the same.
Yeah, but in this way, cylinder in this way correspond to the same dimension, right? Because
the same dimension. Yes. Yes, it should be exactly the same dimension. It's right here. Yeah, so if I'm in d dimensions, then the cylinder is just r cross sd minus 1. And plane is just r to the power d.
Oh, yeah, okay, thank you.
Oh, no worries.
Hi, Sasha. I have 2 naive questions about your previous result you show on the saddle point calculation. You said result is resembles semi-classical calculation.
Yes.
I'm wondering in what sense the form resembles semi-classical calculation, but should I be surprised that it resembles semi-classical calculation? Because the calculation done by Song et al. Was almost in the 0 external momentum limit, right? The epsilon is really small limit, so the result is semi-classical. But here you are not restricting on the on the little external momenta point. So
there are no momenta, right? So I'm just saying that looking at this anomalous dimension that we computed by just computing loops and recasting it in this way, right? You just see that delta is organized as an expansion in lambda with coefficients that are functions of lambda n. This thing suggests that this is semiclassical. By semiclassical, what I mean semiclassical, that this is a computation around some non-trivial saddle. This is what I call semiclassical.
Sure, I see.
And here we demonstrate it, right? I just exponentiated this phi to the n, phi bar to the n, and I have to extremize this specific action, right? And that can be done. Now, instead of extremizing it for arbitrary lambda n, I'm going to use a trick because I do not know how to solve this equation for arbitrary lambda n. This one is valid only for small lambda n. For arbitrary lambda n, I'm suggesting to use a different approach. I'm suggesting to say that instead of computing dimension from the two-point function, from this two-point function, I rather compute energy, the lowest energy on the cylinder, and that would give me the dimension of this operator on the plane.
Sure. Yeah, thanks for explaining. I just want to, the follow-up question about this is, the saddle point calculation is really nice. That was that only for the unbroken theory, or you think it's general for both the broken and the unbroken?
This is not broken or unbroken. This is the theory that I'm considering. There is no math. There is no math term. Nothing is broken.
Right.
This is just conformal field theory at Wilson-Fisher fixed point.
Sure. So okay. So does that okay? I don't know. I thought that would request more towards the unbroken one, but you say there's no proper definition there. So
no,
yeah.
I'm not studying broken theories.
Yeah. Okay. And when you're embedding that on a cylinder with the assumption that the phi n is the lowest state with n charge n, do I have to define the theory here, like to be unbroken, so I can assign charge there? And so that in this mapping, I'm working on an unbroken phase directly, or
the last question I didn't get. So
yeah,
the fact that phi to the n is a nice assumption that this is the lowest lying state, that this is the lowest lying operator. It's look, perturbatively this is true because phi to the n doesn't mix with anything, right? So phi to the n is the lowest one. What else can have charge n and have a different dimensionality? Act with some derivatives on phi to the n, but this one will have larger dimension, right? If you're asking what would happen perturbatively, okay, I'm going to just say that whatever I find for large lambda n, that's what I would call phi to the n. It's just continuity. I just want to match. I find some spectrum for delta phi of n, and going to small lambda n, that matches with the dimensionality of phi to the n. That justifies a posteriori my assumption.
Okay. Thanks for clarifying. Yes. Good.
No worries. So this is my approach. I'm sorry. So this is my action on the cylinder. I have, this math term originates from just non-minimal coupling. It's just phi square r. And what we're looking for is this expression, as I said, and what do we choose as the state psi n? So what we choose is the following state. It's the analog of just a Fourier transform of a state with fixed angle phi, right? So here I just want to fix, this is a state that corresponds to a field rho, or not rho, but if I write my field phi in polar coordinates, rho e to the I chi, then I'm saying the following, that the state with fixed chi and rho is this one. And then I want to consider just a Fourier transform with respect to alpha with in. So, but then this gives me precisely that the charge of this state is m, right? because if alpha shifts by delta alpha, overall thing shifts by in, and this is the manifestation that this state has a charge n. Right. So if I do that, what I have to compute is this matrix element. I plug it here, and then in the end, this is my action original one, and this factor comes from just this projection. Right. What I have to do, I just have to solve this classical equation. Equations of motion, of course, they do not depend on this term because it's just total derivative. However, total derivative imposes boundary conditions, and boundary conditions are those. Yeah, I have to really speed up, but yeah. So the solution is rho is equal to a constant, and chi is actually I mu tau, but that corresponds just to rotating phi. Phi rotates, so phase of phi rotates, and that gives us the charge. The condition to derive this parameter mu comes from here and from imposing the charge, right? And then in the end, mu can be shown to be the following function of lambda n, where f of t is just some function with square roots, but it's regular for lambda n going to 0, and it's actually convergent. What's important here is that now if we plug it back and we look for the dimension, we just have to evaluate the action on the saddle, and this is what we're getting. Now expanding the function for mu, this is mu. For small lambda n, I'm getting the result this, and for large lambda n is that. So for small lambda n, if you compare with what we had before in here, this is exactly this result up to higher order corrections. But also, as I said, this delta can be evaluated for large lambda n as well. And for large lambda n, it becomes lambda n to the power 4/3, which is similar to what Voloshin and Gorsky got for amplitudes. All right, so we can also compute fluctuations, but probably this is not the main issue. But basically, fluctuations allow us to get exactly the anomalous dimension in the following way. It's n-1. In here, it's lambda n square lambda n. This one should be, this one we do not capture yet at this order because we have to go to higher order. We just have to compute lambda times delta 1. But still, we see an agreement with just a perturbative computation, right? But our approach works for arbitrary lambda n. So we can find even corrections to this one. And I think I would rather just say one more thing, that what we have done is to find the anomalous dimension of the lowest lying operator, but we can also find energies, right, for excited states. So for instance, if I take an operator with some spin, not just phi to the n, but say with spin 2, like this, right? Understanding what the dimension of this operator is just building excitations around my vacuum, right? And by doing this, you can also prove that that matches the dimension of this operator computed from perturbation theory, just diagrammatically.
Sash, and this mu and nu are in three-dimensional space. I mean, the indices mu and nu in which
this in 4 minus d.
In 4 right, but 4 minus d, right? So it means that okay.
There are 4 minus d of them. No, then the 4 minus epsilon of them. Yes.
Yeah. 4 minus epsilon. I mean mu and nu. I see. So but you are going along this integer when you're calculating spin. You're implying that it is
look
still
when I say what I call spin in this case is just the rank of this of the tensor, right? It is.
Of course, yeah.
It's just a tensor with 2 indices, symmetric, traceless. This is what I call spin 2.
Right, but it implies certain generalization from where mu and nu goes from, say, from 1 to 3, whatever, some I mean over integer values, right? Or I mean, because symmetric tensor you still implies that certain range of mu and nu, right? Where they run.
Look, Arkady, you have to ask the same question for even for the Lagrangian. What would d mu phi mean?
Yeah, of course, yeah, I agree.
Look, but that means that formally, when I do my computations, I do not care about what my mu and nu is. I'm just saying that this formal structure with two derivatives, mu and nu, symmetrized and subtracted all traces, the dimension of this structure, the dimension of this operator corresponds to just, well, let me call it spin 2 operator, and that corresponds to the excitation around my vacuum.
No, I understand, but I view it in such a way that you have your Lagrangian and you define d or d mu, say 1, 2, 3, whatever, depending on d, and then doing kind of analytical continuation from integer dimension to
non-integer. Yes.
Right. So the same for spin 2. I also would view it the same way. So I start from integer number of dimension, and then think about analytical continuation to non-integer, right? Number of dimensions there.
Sure, but then what's your question?
No, it's just to follow that in this way you are not using here. I see. So it's kind of implied there, right? So
yes.
So I see.
Okay. Yeah, I never go to the limit. Then in the end, d to 4. I'm always in 4 minus epsilon.
Yeah. No, but just the whole definition of epsilon, it implies certain procedure. I agree.
The procedure is exactly as you said. Whenever, look, how dimensional regularization works, you just have to add some other dimensions, then integral split the integral between the physical and unphysical and so on, right?
Okay.
So I think I just have to wrap it up, just the conclusion. So what I try to present is that there is a semi-classical approach, which seems to be straightforward to implement, at least in this conformal field theories, allowing to compute dimensions of operators with large charge for arbitrary lambda n, not only for small lambda n. That result matches with small lambda n expansion that we can compare with just a perturbative expansion around a trivial saddle. For arbitrary lambda n and arbitrary lambda, there is also a procedure, but this one is more of a effective field theory approach, which I can explain a bit, but I think that's that has been already too long. And unfortunately, we're working on this, but the goal is to find similar methods for few to many. And on the one hand, you may say that Son already showed us how to do that. The semi-classical procedure is there, but it's not. I think it's a bit vague, and I would like to have a better approach, or at least to clarify for myself what happens with Son's procedure. Thank you.
All right, thank you, Sasha. Are there any other questions?
Yeah, may I ask a question?
Yep.
Can I ask a question? Sasha, do you understand correctly that it's important for finding of this quasi-classical solution, it's important that it's weakly coupled. I mean, the conformal point is a small deviation from d equal to 4. Is it important?
There are, as usual, two answers. In this procedure, yes, but there is another procedure that tells you how to do that regardless of whether we're close to 4 or not. We can formulate this thing for any conformal field theory, but then there is always a trade-off. So in here, let me just show you one slide here. So this is my Lagrangian of Fluctuations, right?
Yeah.
You see from here that what it corresponds to, this is what you were asking. This pi is just the phase of my field phi. This is the sigma model, what would be a sigma model, right? This R is just a radial mode. Pi is of course massless, but R, because it's a massive guy. And the mass of R is of order mu. If now I go to M extremely large, then mu becomes extremely large. So in this sense, R becomes massive and I can integrate it out. And then I can play the following game. I can say, okay, I'm assuming that the same thing would work for any conformal field theory, but I have to work only in the low energy description of this conformal field theory on the cylinder, in the sense that I integrated out whatever happens at higher energies like radial mode and other states that are massive, and I'm left only with just one parameter, which is chi, which is just the phase of my scalar field. And then the action can be written in the following way. It becomes d chi to the power d, where d is the number of dimension, which is arbitrary, say in 3, d chi cube, plus Ricci tensor coupled with d chi, formally, then Ricci squared d chi d minus 4, and so on and so forth. And this is just effective field theory description. So in this way, you can extend the same result, the same procedure for arbitrary lambda. It's only that in computing anomalous dimensions, not anomalous dimensions, but just the dimensions, you can capture the behavior in N, but the trade-off that we do not know those coefficients, because those are not fixed. Those are just Wilson coefficients of our EFT.
But it is such only in the sector where you consider still large charge, right?
Yes. This is only in large charge. So the idea is the following. For EFT, I'm assuming the following. I have my path integral that I want to compute. I assume that the trajectory that saturates my saddle is something that breaks U1, right? So it's like phi f to the e to the I chi, okay? If U1 is broken, then there should be one goldstone. And this goldstone is precisely my chi. And then I can write consistently effective field theory for my chi, right? And this effective field theory is just that. An expansion runs in 1 over mu, where mu is the derivative of phi, of chi, with respect to time.
I try to ask a different type of questions that maybe it could be relevant. That if we are talking about resurgency, right? This that because it is example where you have this factorial behavior, so it, okay. And in case of resurgency, there is this kind of this stuff about this kind of Laplace transform or Borel transform, whatever you like it, right? To call it where direction as the other, and I wonder that it should be some connection with of what you are doing with this as well, or it's a relevant question.
Just 1 second. No, of course, there should be connection with all of this, but look, I'm saying I'm not trying to guess the function from how it looks. I'm not resumming anything, right? I'm doing just what I did with just a regular integral. In my regular integral, let's go back in the very beginning. In this regular integral, I could have said, yeah, let's take this term plus the next term and so on and so forth, do Borel transform, and then I can hope to reproduce this function. And in this case, it's trivial, it's simple to do, right? And that can be done. I'm doing different procedure. I do not want to resum. I just want the method to do the resummation for me. And the method is, okay, find a different saddle. It's like right? Look, I'm saying just the following, that how does this function look like, right? If n is sufficiently large, small, I mean the whole integrand, the whole integrand in this integral. If n is small, it's peaked around 0, right?
Okay.
If n is large, it's peaked somewhere for large x.
No, Sasha, I understand your point. No, but look, if you can compare with what people are talking about in terms of resurgency, what they are saying that there is, say, like a certain saddle point, like okay, but then and there is perturbative expansion near a saddle point, like say instanton, okay, but then you can consider, I mean, sector without instanton or with 2 instanton or whatever, and then this resurgence refers to relation between these different, stuff. So you found new kind of you found particular saddle point, right? In, say in your method, right? But then I can ask kind of similar questions, maybe in that. Let's say that you have this saddle point. Then, if you like, it is about as iteration of saddle point, if you like.
Okay.
Right?
So, Arkady, if you're asking what should be a relation between, I just want to formulate it in the way that then it would be clear how to approach this question. So, one way to, so basically you're asking, can we know something from the asymptotic series around the trivial saddle? Can we know something about a non-trivial saddle?
Yeah. No,
yes,
of course, right?
Yes, of course we can. But look, first of all, for that I need to know the asymptotic behavior, right? Which I do not know. I just know that my expansion breaks down, right? I can probably play a different role in different game. Obviously, from our result, we can reproduce arbitrary loop result, the leading result in n for any loops, right? Because our result resums lambda m. But I don't think I can say anything more. So in this sense, yes, this is related. Because
No. Okay. Let me ask you in a different way. You have this exponential effect in a sense, right? At the end, right?
Yes.
You still have this. Okay. So like exponent into the power action, you get this because when you're doing your stuff. So then the question I'm asking, it's about, for example, about when it is twice the same action, the other sector, and you are not discussing this one because you kind of in this language you kind of discuss one instanton, but okay, or whatever, one saddle point, but
I do not know of any other saddle points except this one and 0.
Yeah, all right, okay, right. So in this way, you are saying that in some way the in difference with this resurgence, you do not have kind of classification.
In this sense, I do not have like instanton, anti-instanton, then 3 instantons, 1. Yes, this one we do not have, but Arkady, I think that resurgence is not only about this, right?
I got it. Yeah, so
like.
Yeah. But it means that because you are considering this large charge, right? Then it's a different type of, in certain sense, different type of this stuff, right? Because you do not have this kind of probably multiplicity of this saddle points, right? Or iteration of saddle points. Okay, it's what I was wondering about. Thank you.
Okay. My pleasure.
Any other questions?
Hey, Sasha, did you skip the slides on the lambda n bigger than 1 case? You said your calculation is also applicable there, but did you? I thought you skipped that. Did you explain something we learned from that?
No, I don't think I skipped it. It's probably that I rushed through all the slides. Yes. Let me go back. So I just said that what we need to compute is this, right? Then let me just. Let me just give you this simple example how it works. I want to compute this expectation value of my evolution operator, right? Let's do the following, the following thing. I have just a model. I have SO3 invariant system. I have just particle on a sphere, right? Its Hamiltonian is given by just J square over 2I. And imagine I'm asking myself, okay, what is, I want to fix J3 and I want to find the minimal energy in the sector of J3 equal M. Okay, of course you can say, okay, you are silly, because we know the spectrum completely. It's for any LM, the energy is LL plus 1 over 2I, right? But I'm saying, of course, we know that. We just want to understand how the procedure can work. This is just for illustration. And obviously, the lowest energy at fixed M is just given by that, right? How do we do that? Let's do the same thing in using path integral. I want to compute the following matrix element. Okay. I'm taking a state with fixed charge M. In this case, by charge, I mean J3. And I compute between theta F, theta I, and MM. That can be written just like this, right? Here I have a derivative I M phi dot. It comes only from phi F minus phi I. And I have to extremize this action. What is my solution? The solution, let me choose both theta F and theta I to be pi over 2, then theta stays constant. What does it correspond to? It corresponds just to particle spinning on the equator, right? But in Euclidean, that becomes minus I tau, right? Plugging it back to the action, this is what I get. In the leading order, it's M squared over 2I times T, the difference between TF minus TI. What about fluctuation? Expanding in theta and phi, in delta theta and delta phi. There is a gapped mode M over I, which corresponds to theta. Computing correction to the ground state, I'm getting M squared over 2I. This is just the leading term. M over 2I, one loop. Constant comes from two loops, which is not interesting, right? And all the rest, they vanish. Ta-da, I reproduce the full result. The fact that it vanishes is just a coincidence, right? It may have well be that corrections would be 1 over M plus 1 over M squared and so on and so forth. So this is the way it works. And it works for arbitrary M, right? The same now I do here. I take my system on a cylinder, right? And I need to introduce some states here that I want to project on. So basically, I'm just saying that if I take any state with charge M, right, then for large Euclidean time, that would project itself onto the lowest lying state, which is delta phi M, right? And here I'm not saying anything about what should be lambda M, right? It's not restricted. I'm doing similarly to what we did before, just the Fourier of fixed phi. This is what I said before. I take this specific state, and then in the end, it boils down to just extremizing this action. But lambda M here is not fixed. It can be arbitrary thing, right? That can be solved for any lambda n. Mu becomes some specific function of lambda n, and this function is given by this expression. And now plugging it back, you're getting this. It's n over 2, blah, 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 just as a function of mu. And this mu is function of lambda n, arbitrary. Now, for small lambda n, it can be expanded like this. For large lambda n, it's expanded like that.
I see. Yeah, thanks. Yes.
Okay.
Basically, your calculation is based upon the states and the correlation there. You don't have any explicit expression around lambda O lambda n, right? So that's why your final result is applicable for lambda n bigger than 1.
Yes.
Yeah. Good. Thanks.
It works for arbitrary lambda n, as long as lambda is small.
Sure.
Yeah. My theory is weakly coupled.
Okay, any other questions? If not, I'll start.